Something emerged from behind the Sun that shouldn't exist the way it does. On October 29th, 2025, an object we've been tracking for months passed through its closest approach to our star a moment called perihelion, and survived. That alone isn't shocking. Comets do this. But what's happening right now, in the hours and days since that passage, is creating quiet tension in observatories around the world. Not panic, not alarm, just focused attention on data that refuses to behave exactly as predicted. The object is 3I Atlas, and if you've been following this story, you know it's not from here. It came from interstellar space, passed through our solar system's neighbourhood, and 3 days ago faced the most intense thermal stress of its journey. It survived intact. No fragmentation, no catastrophic breakup. That's good news, right? That's what we expected. Except now, as it moves away from the Sun and becomes visible again to Earth-based telescopes after weeks hidden in solar glare, something nobody predicted with complete confidence is unfolding in real time. It's not dimming the way it should. Its chemical signature is shifting faster than some models anticipated. Its activity patterns, the jets and streamers of gas and dust, are revealing structures we couldn't see before perihelion, and its trajectory, now measured with far greater precision thanks to improved observational geometry, is telling us things about its mass, its composition, its behaviour under solar heating that challenge our initial assumptions. Let me be clear about what different means here, because I know how these stories get twisted. This isn't about aliens. It's not about propulsion systems or artificial structures or signals beaming toward Earth. The data we're seeing is consistent with natural cometary behaviour, but it's the complex, messy, unpredictable kind of natural behaviour that reminds us how little we actually understand about objects formed around other stars, stored in interstellar cold for potentially billions of years, then suddenly thrust into the intense radiation environment near our Sun. Right now, 3I Atlas is approximately 1.4 astronomical units from the Sun, about 210 million kilometres, and moving outbound at 44 kilometres per second relative to our solar system's centre of mass. Its solar elongation has increased to 18 degrees, which means telescopes can finally observe it without the Sun's overwhelming glare interfering. And what they're seeing in these early post-perihelion observations is forcing astronomers to revise brightness curves, update outgassing models, and refine predictions for what happens next. It passes Venus at a distance of 0.65 astronomical units. That's not particularly close, 97 million kilometres, but it matters for trajectory refinement. Then, on December 19th, it makes its closest approach to Earth, 1.80 astronomical units, or 270 million kilometres away. That's when amateur astronomers with decent equipment will have their best shot at seeing an interstellar visitor with their own eyes. And finally, on March 16th, 2026, it swings past Jupiter at just 0.36 astronomical units, its closest encounter with any planet in our solar system, before heading back into the darkness between stars, probably forever. But all of that future timeline depends on understanding what's happening right now, because the 3 days since perihelion have produced observations that don't quite match the predictions built from 3 months of pre-perihelion data. Not wildly off, not inexplicably different, just different enough that scientists are recalculating, reassessing and asking new questions about what perihelion heating actually did to this object's interior structure. Think about what 3I Atlas experienced on October 29th. For billions of years, maybe since before Earth even formed, this object drifted through interstellar space at temperatures barely above absolute zero, 3 degrees Kelvin, cold beyond anything we experience in daily life. Then it fell into our solar system's gravity well, accelerated toward the Sun, and at perihelion absorbed 770 watts per square metre of solar radiation. That's not as extreme as the sun-grazing comets that skim just hundreds of thousands of kilometres above the solar surface and either vaporise or emerge transformed. But it's enough thermal stress to crack open structural weaknesses, to sublimate volatile ices buried metres deep, to change the object fundamentally. And now we're watching those changes unfold in real time. The brightness data coming from observatories like the Nordic Optical Telescope, Palomar, and amateur networks coordinating across continents shows an object that should be dimming faster as it moves away from the Sun's heat. Standard cometary physics says brightness should drop following an inverse power law distance to the negative third or fourth power. Pre-perihelion observation suggested 3. IATLAS followed that law almost perfectly, with an exponent around 3.8. But post-perihelion, it's dimming more slowly, about 1 magnitude brighter than predictions. That excess brightness has natural explanations, we'll explore them in detail, but it wasn't confidently predicted before perihelion. The chemical signatures are shifting too. Spectroscopy. Before perihelion showed carbon dioxide dominating the outgassing, with water playing a secondary role and various organic molecules producing weak emission lines. Now, 3 days after perihelion, water signatures are strengthening relative to CO2. That matches expectations for cooling carbon dioxide sublimates at lower temperatures than water, so as surface temperature drops, CO2 production should decrease faster. But the magnitude of the shift suggests subsurface layers with different composition than the surface are now exposed and actively outgassing. Perihelion heating penetrated deeper than some models predicted. You need to understand something fundamental here. When we talk about predictions and models and expectations, we're not talking about certainties. We're talking about best guesses built from limited data about an object type we've only studied twice before, Oumuamua in 2017 and 2I/Borisov in 2018-2019. Oumuamua gave us almost nothing it was detected after perihelion, already leaving, and produced no clear cometary activity. 2I/Borisov was better active comet, well observed, but its perihelion was 2.0 astronomical units, much farther from the Sun than 3I Atlas. So this is only the second time we've watched an interstellar comet pass close to the Sun with comprehensive instrumentation tracking every phase of its journey. And what we're learning in these early post-perihelion days is that reality is more complex than our models captured. That's not failure. That's science working exactly as designed to make predictions, test them against observation, revise understanding, make better predictions. The story didn't end on October 29th when 3I Atlas survived perihelion. In many ways, the most interesting chapter is just beginning. Let's talk about survival, because that word carries weight in this context. When astronomers say 3I Atlas survived perihelion, they're not being dramatic. They're confirming something that genuinely had uncertainty attached to it. Comets fragment, comets die. And when you're dealing with an object that's been thermally isolated for billions of years, suddenly exposed to intense solar radiation, structural failure is a real possibility. Look at the historical record. In November 2013, Comet Ison approached the Sun on what should have been a spectacular trajectory perihelion at just 0.012 astronomical units, barely 1.8 million kilometers above the solar surface. Astronomers predicted it might become visible in daylight, one of the brightest comets in decades. Instead, it disintegrated. SOHO spacecraft watching the approach saw the nucleus break apart under thermal stress and tidal forces. What emerged from behind the Sun was debris, rapidly dispersing, never to reform. ISON didn't survive. In December 2011, Comet Lovejoy, formerly C/2011 W3, dove even closer to the Sun, at 0.0055 astronomical units. That's 820,000 kilometers, close enough that surface temperatures exceeded 2,000 degrees Celsius. Nobody expected survival. But Lovejoy emerged, intact but transformed, trailing a spectacular tail visible to the naked eye from the southern hemisphere. It survived barely but lost tremendous mass. Post-perihelion observations showed an object fundamentally altered by its passage, with surface layers stripped away and internal structure exposed. Now consider 3I Atlas. Its perihelion on October 29th, 2025, was 1.356 astronomical units, about 203 million kilometers from the Sun. That's nowhere near sun-grazing territory. It's actually a moderate distance, similar to Mars's orbit. But here's what makes it interesting. This object spent billions of years at 3 degrees Kelvin, interstellar cold. The kind of cold that freezes carbon dioxide solid. The kind of cold that turns water into ice harder than steel. The kind of cold that allows extremely volatile substances, things that would evaporate instantly at Earth temperatures, to remain stable indefinitely. Then suddenly, over the course of months as it fell toward the Sun, temperatures rose, not gradually enough for gentle adaptation, fast enough on cosmic timescales to create thermal stress differentials through the nucleus. The The surface heats and begins outgassing while interior layers remain frozen. This creates pressure, structural tension, zones of weakness where different temperature regimes meet. And if the nucleus is a loosely bound rubble pile, many comets are those zones of weakness become fracture planes. At perihelion, 3I Atlas absorbed 770 watts of solar radiation per square metre. For context, Earth at its distance receives about 1,360 watts per square metre, the solar constant. So 3I Atlas experienced roughly 57% of the solar intensity Earth does, but on a surface that had never experienced anything close to that level of heating. The surface temperature would have spiked to approximately 270 Kelvin minus 3 degrees Celsius. That's right at water's freezing point, though in the vacuum of space, ice sublimation dynamics are different than terrestrial melting. That thermal stress was sufficient to potentially trigger fragmentation if structural weaknesses existed. Comet Schwarzmann-Wachmann 3, for example, broke into multiple fragments not during perihelion, but during an earlier passage when thermal stress activated cracks that had formed over previous orbits. Comet Shoemaker-Levy 9 famously fragmented when Jupiter's tidal forces exceeded its structural integrity during a close approach in 1992. Then the fragments returned in 1994 to impact Jupiter in one of the most spectacular astronomical events ever witnessed. So when observers confirmed on November 1st and 2nd that 3I Atlas emerged from perihelion intact, no fragmentation detected, no secondary nuclei, no debris cloud expanding away from a primary body, that told us something important about its internal structure. It means one of several things. Either the nucleus has significant tensile strength, possibly from organic tars or complex carbon compounds that act as cementing agents holding the structure together, or the nucleus has a thick insulating dust mantle, a layer of dark, porous material on the surface that absorbed solar heating but conducted it slowly into the interior, preventing the rapid temperature differential that causes fracturing. Or the composition is more homogeneous than typical solar system comets, without the distinct layers and internal weaknesses that create fracture planes. Compare this to 2I/Borisov, the previous interstellar comet. It passed perihelion at 2.0 astronomical units in December 2019 and survived intact, though observations did detect a possible fragmentation event or major outburst in March 2020, several months after perihelion, which some researchers interpreted as delayed structural failure from perihelion thermal stress. The fact that 3I Atlas has now been observed for 3 days post-perihelion with no signs of fragmentation is encouraging. It suggests the nucleus is either structurally coherent or any fractures that formed haven't yet led to separation. But survival means more than just not breaking apart. It means continuing to function as an active comet. And here's where post-perihelion observations get interesting. 3I Atlas didn't just survive, it remained active. Coma and tail structures persist. Outgassing continues. The jets of gas and dust that indicate sublimation from discrete active regions on the surface are still producing observable effects. This wasn't guaranteed. Some comets experience perihelion and emerge dead, their volatile ices exhausted. Surface sealed by a dust mantle too thick for further sublimation. Activity ceasing as they transform from active comets into inert asteroids. The fact that 3I Atlas remains active tells us volatile reserves weren't depleted by perihelion. It tells us subsurface ice layers are still accessible, still sublimating, still driving outgassing, and it tells us we're going to continue getting data spectroscopic, photometric, morphological, as it moves outbound through November, December, and into 2026. Dead comets provide one-time structural information. Active comets provide ongoing compositional and dynamical data across changing solar distances and temperatures. November 1st observations from ground-based telescopes that finally had clear lines of sight after weeks of solar conjunction confirmed coma diameter approximately 150,000 kilometers larger than Jupiter and tail extension beyond 800,000 kilometers. Both consistent with pre-perihelion observations, though detailed morphology is still being analysed. The Nordic Optical Telescope reported no obvious fragmentation features, no secondary condensations in the coma that would indicate pieces breaking off, no anomalous brightness distributions that would suggest structural failure. This is what survival looks like in cometary science. Not just physical integrity, but continued activity, ongoing evolution, an object that remains dynamic and scientifically productive rather than a static corpse drifting through space. And it sets the stage for everything that follows because an active comet tells us stories about its composition, its interior structure, its formation environment around another star. A dead comet takes those stories to the grave. So yes, 3I Atlas survived. That was the best-case scenario, and reality delivered. But survival alone doesn't explain why post-perihelion observations are revealing complexities that pre-perihelion models didn't fully capture. For that, we need to look at what's happening to its brightness, and this is where difference starts to become quantifiable. Numbers don't lie, but they do surprise. And right now, the brightness numbers coming from 3I Atlas are telling a story that wasn't fully written in pre-perihelion predictions. This isn't about dramatic flaring or unexplained luminosity. It's about subtle deviations that become significant when you understand the physics involved. It's about an object that should be dimming faster as it moves away from the sun, and it is dimming, just not at quite the expected rate. Let me walk you through the physics first, because this matters. Comet brightness depends primarily on two things: reflected sunlight from the solid nucleus and dust particles in the coma, and scattered sunlight from gas molecules in the coma. Both scale with heliocentric distance how far the comet is from the sun, but in nonlinear ways. The standard model uses a power law. Brightness is proportional to distance to the negative in power, wherein typically ranges from 3 to 4 for active comets. An n value of 4 means if you double the distance from the sun, brightness decreases by a factor of 16. An n value of 3 means brightness decreases by a factor of 8 for that same doubling. Pre-perihelion observations of 3I Atlas from July through late October tracked brightness carefully as it approached the sun. Multiple observatories contributed data points, photometric measurements in visible wavelengths, filtered observations isolating dust versus gas contributions, time series data revealing short-term variations. When astronomers fitted that data to the standard brightness law, they derived an n value around 3.8. That's normal for active comets. It suggested outgassing responded predictably to solar heating, with sublimation rates increasing as temperature rose. Based on that n equals 3.8 relationship, predictions for perihelion brightness were made. At perihelion on October 29th, at 1.356 astronomical units from the Sun, 3I Atlas should have reached approximately magnitude plus 11.0, bright enough for serious amateur telescopes, faint enough to require good technique and dark skies. Then as it moved outbound, brightness should have dimmed following that same relationship. By November 2nd, at approximately 1.42 astronomical units, predicted magnitude was around plus 12.5 to plus 13.0, depending on how quickly post-perihelion cooling reduced outgassing rates. But observations on November 1st and 2nd show something different. Multiple independent sources report brightness approximately plus 11.5 to plus 12. 0 about 1 magnitude brighter than the conservative predictions, and half a magnitude brighter than optimistic ones. 1 magnitude might not sound like much, but in astronomical terms it's significant. Magnitude is logarithmic, each magnitude represents a brightness factor of 2.512. So 1 magnitude difference means 2.5 times more light. That's not a subtle deviation, that's a measurable excess that demands explanation. Before we go further, let's be clear about what this is not. This is not evidence of an internal light source. It's not suggesting electrical activity or phosphorescence or anything beyond conventional cometary physics. The brightness is still entirely consistent with reflected and scattered sunlight, but the amount of sunlight being reflected and scattered is higher than predicted, which means something about the outgassing behaviour, dust production, or coma structure differs from pre-perihelion models. Explanation 1. Perihelion heating activated subsurface volatile reservoirs that pre-perihelion models underestimated. Think of the nucleus as layered. The surface experiences direct solar heating and begins outgassing as temperature rises. But heat doesn't stop at the surface, it conducts inward, creating a thermal wave that penetrates deeper over time. The speed of that penetration depends on thermal conductivity, which for cometary material is notoriously difficult to measure. Estimates range from very low conductivity essentially insulating to moderately higher values if the material has some structural connectivity. If thermal conductivity is on the lower end, heat penetrates slowly, maybe centimeters per day. If it's higher, meters per week aren't unreasonable. By perihelion, after months of increasing solar heating, That thermal wave could have penetrated 1 to 2 meters into the nucleus. And if subsurface layers contain volatile ice water, carbon monoxide, methane that were protected from space weathering, and remain relatively pristine, those layers would begin sublimating as the thermal wave reached them. Here's the key. Subsurface sublimation can create pressure. Gas generated below the surface has to escape through cracks, pores, or by breaking through weakened surface layers. When it does, it carries dust with it more efficiently than surface sublimation alone. That increases dust production rates. More dust in the coma means more total surface area reflecting sunlight. The coma becomes more effective at scattering light even if the absolute amount of gas hasn't increased proportionally. Result: brightness higher than predicted. Explanation 2. The dust-toga's ratio changed post-perihelion. Pre-perihelion observations gave rough estimates of how much dust versus gas 3i Atlas was producing. Spectroscopy measures gas directly through emission lines. Dust is inferred from continuum brightness, the baseline light level after subtracting all the spectral lines. The ratio matters because dust dominates visible brightness, while gas provides compositional information. If perihelion heating broke down surface dust layers, exposing more erodible material, dust production could increase without proportional gas increase. Or conversely, if new gas sources activated but couldn't carry as much dust due to lower velocity, the ratio shifts the other way. Post-perihelion spectroscopy, which we'll discuss in depth later, is starting to provide clues about this ratio. Preliminary reports suggest dust contribution to total brightness may be slightly higher post-perihelion than pre-perihelion measurements indicated. If confirmed, that would explain excess brightness. It's not that the comet is fundamentally more active, it's that the activity is producing more visible dust relative to transparent gas. Explanation 3. Rotation axis orientation changed, or we're seeing different active regions. Most comets rotate and most have heterogeneous surfaces. Some regions are more active than others, either due to compositional differences, ice concentration variations, or surface texture affecting how efficiently sublimation occurs. If 3i Atlas has a rotation period of several hours still not precisely measured but inferred from short-term brightness variations, then as it rotates, different regions point toward the Sun at different times. Pre-perihelion, we were seeing one set of active regions. Post-perihelion, viewing geometry changed and perhaps more active regions are now preferentially pointing toward Earth. That would make the comet appear brighter from our perspective, even if total outgassing hasn't changed. It's an observational bias, not a physical change in the object, but it produces the same brightness excess in our data. Explanation 4. The pre-perihelion brightness law was incomplete. This is the humbling possibility that our models, built from 3 months of data, didn't capture all the variables. Comets are complex. Their brightness doesn't always follow simple power laws, especially during periods of changing activity. Some comets show outbursts, sudden temporary brightness, increases caused by collapse of subsurface voids or fracturing that exposes fresh ice. Others show delays between temperature changes and brightness changes, because thermal inertia prevents instantaneous response to solar heating changes. If 3i Atlas has significant thermal inertia, if the nucleus is large enough or thermally massive enough that temperature changes lag behind solar distance changes by days or weeks, then peak brightness might occur after perihelion rather than at perihelion. That would explain why it's brighter now than simple extrapolation predicted. The object is still responding to perihelion heating, even though it's now moving away from the Sun. There's precedent for this. Comet Hale-Bopp, observed extensively in 1996 to 1997, showed complex brightness behaviour that required sophisticated models accounting for multiple volatile species with different sublimation temperatures, rotating nucleus with distinct active regions, and dust production varying with heliocentric distance in non-power law ways. It reached peak brightness weeks after perihelion. Solar system comets do this. It's plausible an interstellar comet does too. So we have natural explanations, multiple natural explanations for why 3i Atlas is about 1 magnitude brighter than conservative predictions. None require exotic physics. None suggest artificial enhancement. They're all variations on the theme of comets are complicated and our models from limited pre-perihelion data didn't capture every detail. That's not failure. That's exactly what we should expect when studying an object from around another star for the first time at this distance. But here's what makes it scientifically valuable. The brightness excess is measurable, quantifiable, and will continue to be tracked as 3i Atlas moves outbound. By December, when it approaches Earth, and observational conditions improve dramatically, we'll have months of post-perihelion brightness data. That long baseline will allow much better modelling of what actually controls its brightness thermal inertia, dust production rates, rotation effects, subsurface activation, or combinations thereof. And that improved model won't just tell us about 3I Atlas, it will improve our understanding of interstellar comets in general. The next Visitor 4I/whatever it will be named will benefit from lessons learned here. We'll make better predictions because reality corrected our first attempts with this object. That's the scientific method functioning as designed. Predict, observe, revise, predict better. But brightness isn't the only thing evolving in unexpected ways. The trajectory, the actual path through space, is becoming clearer with each post-perihelion observation, and that precision is revealing details about mass, composition, and forces we couldn't resolve before October 29th. Trajectory is destiny for objects travelling through our solar system, and right now the trajectory of 3I Atlas is being refined with precision that simply wasn't possible a week ago. This isn't because the object changed course, it's because observational geometry improved dramatically once it emerged from solar conjunction, and because multiple observations from different vantage points allow triangulation that narrows uncertainty margins from thousands of kilometers down to hundreds. Let's start with what trajectory actually means in this context. When astronomers track 3I Atlas, they're measuring its position against background stars at specific times. Those measurements, combined with known positions of Earth and other planets, allow calculation of orbital elements, mathematical parameters that describe the size, shape, orientation, and timing of the object's path through space. The key parameters are semi-major axis, related to orbital energy, eccentricity, how elliptical versus circular, inclination, tilt relative to Earth's orbital plane, longitude of ascending node, where the orbit crosses the ecliptic plane, argument of perihelion, orientation of closest approach, and time of perihelion passage. For 3I Atlas, the most important parameter is eccentricity. Objects with eccentricity less than 1.0 are bound to the Sun. They're on elliptical orbits that bring them back periodically. Eccentricity exactly 1.0 means parabolic orbit barely unbound, will never return. Eccentricity greater than 1.0 means hyperbolic definitively unbound, came from interstellar space and will return there. Pre-perihelion measurements clearly established 3I Atlas has eccentricity greater than 1, confirming interstellar origin. But the precise value matters because it determines incoming velocity and, after accounting for gravitational interactions with planets, outgoing velocity. Before perihelion, when 3I Atlas was approaching through late summer and early October, it was relatively easy to observe good separation from the Sun, decent brightness, positioned in evening sky. Those observations established eccentricity approximately 1.045, with uncertainty margins around plus or minus 0.003. That translated to an incoming velocity relative to the solar system barycenter, the centre of mass around which Sun and planets orbit, of about 44 kilometers per second. That's fast, but not exceptionally so. Oumuamua had incoming velocity around 26 kilometers per second, while 2I/Borisov came in at about 32 kilometers per second. Then came perihelion, and for nearly 3 weeks from mid-October through early November, observational conditions deteriorated. Solar conjunction means the object is near the Sun as seen from Earth, lost in glare, unobservable by ground-based telescopes. Space-based assets like SOHO and STEREO spacecraft have sun-gazing instruments, but optimized for the solar corona, not for faint comets. A few observations were possible from spacecraft with different viewing angles, but precision suffered. Now, post-perihelion, 3I Atlas has emerged into observable sky again. Solar elongation increased to 18 degrees on November 2nd, and continues improving daily. By mid-November it will reach 30 degrees easily observable in dark sky, a couple hours after sunset from northern hemisphere mid-latitudes. And crucially, observations now come from different geometry than pre-perihelion. Before perihelion, Earth and 3I Atlas were on same side of Sun. Now they're on opposite sides. That change in viewing angle combined with time elapsed allows much better determination of all orbital elements. Post-perihelion observations from November 1st and 2nd, incorporating data from Nordic Optical Telescope, Palomar and amateur networks, have refined eccentricity to approximately 1.046 with uncertainty margin now around plus or minus 0.001. That's 3 times better precision than pre-perihelion. It confirms interstellar origin beyond any reasonable doubt. Eccentricity is definitively greater than 1.0, even accounting for measurement uncertainty, and it allows precise calculation of encounter velocities at upcoming planetary flybys. But here's where it gets interesting for physics rather than just geometry. Pure gravitational trajectory would follow Kepler's laws perfectly. An object subject only to the sun's gravity traces a perfect conic section, and once you measure enough positions, you can calculate past and future positions with arbitrary precision, limited only by measurement accuracy. But 3i Atlas isn't following pure gravitational trajectory. It's outgassing, and outgassing creates forces. Think of it this way. When ice sublimates on the comet's surface, gas molecules expand away at speeds of a few hundred meters per second fast compared to the comet's orbital velocity. But the important part is directionality. If outgassing happens uniformly across the entire surface, forces cancel out. Gas streaming in all directions produces no net force. But outgassing doesn't happen uniformly. It's strongest on the day side, weaker or absent on the night side. It's concentrated at active regions where fresh ice is exposed. And if the nucleus is rotating, which almost certainly it is, the pattern of outgassing relative to the Sun changes over the rotation period. All of this creates net forces called non-gravitational accelerations in the technical literature. These forces are tiny compared to solar gravity, but measurable over weeks and months. They cause the actual trajectory to deviate slightly from pure Keplerian orbit. By measuring those deviations and comparing them to models of outgassing, astronomers can infer properties they can't measure directly: rotation axis, orientation, distribution of active regions, even constraints on nucleus mass. Pre-perihelion observations detected non-gravitational acceleration in 3i Atlas. Models suggested it was consistent with typical cometary outgassing radial force component, pushing away from Sun, and transverse component along velocity direction, either speeding up or slowing down depending on whether active regions lag or lead the subsolar point as nucleus rotates. The magnitude was small, corresponding to about 10 to the 7th meters per second, squared barely a trillionth of Earth's surface gravity, but integrated over months, enough to shift position by hundreds of kilometers compared to pure gravitational trajectory. Post-perihelion observations are now refining those non-gravitational parameters. With 3 additional days of position data, and with viewing geometry changed, fits improve. Preliminary analysis suggests non-gravitational acceleration may have increased slightly post-perihelion, consistent with higher outgassing rates closer to Sun. This is expected. Closer to Sun means more heating, means more sublimation, means stronger jet forces. By December, when Earth approach provides intense observational coverage, non-gravitational parameters will be known with high precision. Why does this matter beyond academic precision? Because non-gravitational forces tell us about the interior. A solid, monolithic nucleus would produce simple outgassing patterns, single rotation period, stable active regions, predictable force variations. A rubble pile nucleus, loose aggregate of fragments weakly bound by gravity, might show more complex behaviour if fragments rotate relative to each other, or if internal structure channels outgassing in unpredictable ways. A nucleus with a large volatile reservoir would show strong, sustained non-gravitational acceleration. A depleted nucleus approaching end of life would show weak, erratic acceleration. 3i Atlas appears to fall in the middle, moderate non-gravitational acceleration, stable over weeks, predictable within models. That suggests coherent nucleus with identifiable active regions and stable rotation, exactly what we'd expect for an object that survived perihelion intact. If it were fragmenting or structurally unstable, we'd see erratic trajectory deviations as pieces separated and outgassing patterns changed. There's also planetary defense relevance here, though it's subtle. 3i Atlas poses zero collision risk to Earth or any planet. Its trajectory is well determined and misses everything by comfortable margins. But it's a test case for tracking protocols. The International Asteroid Warning Network, IAWN, and national space agencies coordinate observations of potentially hazardous objects. Most are asteroids with no outgassing, so pure gravitational dynamics, but some are dormant comets that might activate if disturbed, or if they pass close enough to Sun to trigger sublimation. Understanding how outgassing affects trajectories is essential for accurate hazard assessment. 3i Atlas provides real-world data for those models. It's an object with measurable outgassing, well-observed trajectory, and no danger-perfect test case for validating tracking software and prediction accuracy. The fact that post-perihelion trajectory matches predictions within refined error bars demonstrates that current models work. If it had deviated wildly from predictions, that would indicate gaps in understanding that could be dangerous when assessing an actual threat. Tomorrow, November 3rd, the Venus flyby provides another data point. Venus itself has no active spacecraft positioned for comet observation, but the flyby geometry means Earth-based telescopes see 3i Atlas from a different angle relative to Venus. If trajectory predictions are accurate, the comet should pass Venus at the predicted time and distance. Observations confirming that will further tighten orbital parameters, and the gravitational influence of Venus, though tiny at 0.65 astronomical unit separation, is measurable. It produces a small perturbation that allows independent mass estimation of the comet if position is measured precisely enough before and after flyby. Mass is the big unknown. We know size approximately maybe 24 kilometers diameter based on brightness and assumptions about reflectivity. But mass requires knowing density, and density requires knowing composition and internal structure. Is it dense rock and ice like a typical solar system comet? Is it fluffy, porous ice with almost no rock? Is it something different, reflecting formation conditions around another star? By March 2026, when 3i Atlas passes Jupiter at much closer range, gravitational perturbation will be larger and mass determination more precise, but that's months away. Right now, trajectory refinement tells us the path forward is clear literally. We know where 3i Atlas will be in December for Earth approach, in March for Jupiter flyby, and when it will fade beyond detection capability as it heads back to interstellar space. That timeline is set. What's not fully determined is what that object actually is, its composition, its internal structure, its formation history. And for that, we need to look deeper than position and velocity. We need to analyze the light it produces, the chemical signatures in its spectrum, the fingerprints of its creation around another star billions of years ago. If trajectory tells us where an object has been and where it's going, spectroscopy tells us what it's made of and what processes are currently active. And right now, the spectroscopic signature of 3i Atlas is shifting in ways that reveal subsurface composition we couldn't access before perihelion. This is where post-perihelion observations become truly revealing, because perihelion heating didn't just warm the surface, it penetrated deep enough to expose chemical layers that spent billions of years hidden beneath an insulating crust. Spectroscopy works by splitting light into its component wavelengths, essentially a high-resolution rainbow, and analyzing which wavelengths are present, absent, or enhanced. When molecules in the cometary coma absorb sunlight, electrons jump to higher energy states, then fall back down, emitting light at specific characteristic wavelengths. Each molecule has unique emission lines, a fingerprint that identifies its presence and allows measurement of its abundance. Water emits strongly in the ultraviolet and in specific visible wavelengths. Carbon dioxide has characteristic infrared lines. Carbon monoxide, cyanogen, diatomic carbon all produce distinct signatures. Pre-perihelion spectroscopy of 3i Atlas, conducted from July through October as it approached the Sun, painted a clear picture. Carbon dioxide dominated outgassing. The CO2 emission lines were strong, easily detected, indicating substantial sublimation. Water signatures were present but secondary detectable, measurable, but not the primary outgassing species. This was interesting because it differed from typical solar system comets, observed at similar distances. Most comets become water-dominated by the time they reach 1.5 astronomical units from the Sun. But 3i Atlas showed CO2 strength, suggesting it was driving activity even as solar heating increased. There were also organic molecule signatures CN, cyanogen, C2, diatomic carbon, C3, triatomic carbon, indicating complex carbon chemistry. These molecules don't exist in interstellar space. They form when larger organic compounds, things like HCN, hydrogen cyanide, hydrocarbons, maybe even amino acids or sugars, get broken apart by ultraviolet sunlight in the coma. So their presence tells us the nucleus contains complex organic material, common in solar system comets and apparently in interstellar comets too, and there was nickel. Spectroscopic detection of nickel emission lines in May through July, when 3i Atlas was still beyond 2 astronomical units from the Sun, was remarkable because nickel requires high temperatures to vaporize above 700 Kelvin typically. The prevailing explanation is that nickel atoms are embedded in or bonded to organic compounds that sublimate at much lower temperatures, then get released and ionized by sunlight, producing the observed emission. This nickel detection in both Oumuamua's trajectory analysis, indirectly, and Tua/Borisov, directly, has become a signature of interstellar visitors, possibly indicating universal presence of metallic components in comets, regardless of origin. That was the pre-perihelion baseline: CO2 dominated, water secondary, organics present, nickel detected. Now, 3 days post-perihelion, spectroscopy reveals changes. Multiple observatories acquiring post-perihelion spectra report water emission lines strengthening relative to CO2. The ratio hasn't flipped dramatically. CO2 is still abundant, but water/CO2 ratio has increased measurably compared to pre-perihelion values. This is textbook cometry evolution, and it tells a thermal story. Carbon dioxide ice sublimates at lower temperatures than water ice. At one point, 5 astronomical units from the Sun, equilibrium temperature for a dark surface is around 200 Kelvin well above CO2, sublimation point of 195 Kelvin at low pressure, but still below water sublimation point of 273 Kelvin for pure ice. However, dirty ice water mixed with dust and organics can sublimate at lower temperatures because surface contaminants absorb sunlight and locally heat ice patches, so both species can be active simultaneously, with relative rates depending on temperature, ice mixture, and surface exposure. Before perihelion, while approaching and heating up, CO2 dominated because surface layers were rich in CO2 ice, possibly a surface frost deposited during millions of years in interstellar space, where CO2 would condense from trace interstellar gas or from outgassing during previous perihelion passages if 3I Atlas had orbited another star before being ejected. As temperature rose toward perihelion, CO2 sublimation accelerated faster than water because it's more volatile. Now, post-perihelion, surface temperature is dropping as the comet moves away from Sun. But subsurface temperature lags thermal inertia, means heat absorbed at perihelion is still diffusing inward and takes time to radiate away. This creates an interesting situation. Surface may be cooling enough that CO2 sublimation is decreasing, but subsurface layers 12 meters deep are now at their maximum temperature, and those layers appear to be water-rich. When that subsurface water ice sublimations, gas must escape through cracks, pores, or by breaking through surface. As it does, it carries some of the remaining surface CO2 with it, but the bulk of new outgassing is water-dominated. Result: water emission lines strengthen. CO2 lines remain substantial but don't increase proportionally. Ratio shifts toward water dominance. Over coming weeks and months, if this trend continues, 3I Atlas may evolve into a water-dominated outgasser like typical solar system comets, or it may stabilize at some mixed ratio reflecting its unique composition. What makes this scientifically valuable is the comparison between surface and subsurface composition. Surface composition of interstellar comets might be modified by cosmic ray exposure, ion bombardment, and deposition of interstellar material during millions or billions of years traveling between stars. Subsurface composition, protected from those effects, better reflects the original formation conditions around the parent star. By watching how the spectroscopic signature evolves as perihelion heating exposes deeper layers, we're effectively drilling into the comet without needing a spacecraft impact or sample return mission. There's more in the spectra beyond water and CO2. The organic molecule signatures CN, C2, C3 are showing changes too. Preliminary reports suggest C2 and C3 emission lines are strengthening post-perihelion. These molecules form from photodissociation of larger parent molecules, so stronger emission could indicate either increased production of parent organics or different parent molecules with different photodissociation yields becoming dominant. One possibility: pre-perihelion outgassing released simpler organics, things like methane, ethane, HCN that produce standard organic daughter products. Post-perihelion, deeper subsurface layers containing more complex organics, maybe polycyclic aromatic hydrocarbons, long-chain hydrocarbons, or even organic polymers are being exposed and breaking down under solar ultraviolet, producing different or enhanced C2 and C3 signatures. If confirmed, This would suggest compositional layering in the nucleus, simpler organics near surface, complex organics, deeper mirroring layering observed in some solar system comets. Nickel emission continues to be detected, which is reassuring for the hypothesis that nickel is distributed throughout the nucleus, not just surface contamination. If nickel were only on the surface, perihelion heating might have vaporized or exhausted those deposits, and post-perihelion nickel emission would cease. The fact that it persists suggests nickel-bearing material extends into subsurface layers now being exposed by ongoing sublimation. There's also an ammonia question. Ammonia, NH3, is a volatile that sublimates at temperatures similar to water and is common in outer solar system objects. Detection of ammonia in comets from the Oort cloud. The distant reservoir of comets surrounding the solar system has been used to infer formation temperatures and locations. Some models predict interstellar comets should have ammonia if they formed in cold outer regions of protoplanetary disks, but ammonia is hard to detect spectroscopically because its primary emission lines overlap with other species, and it photodissociates quickly in sunlight. Pre-perihelion searches for ammonia in 3I Atlas were inconclusive, some possible weak detections, but nothing definitive. Post-perihelion spectra are being analysed specifically for ammonia signatures. If detected now, when subsurface ices are being exposed, it would support models that place 3I Atlas formation in cold outer regions similar to our Kuiper belt. If ammonia remains absent or weak, it might indicate formation closer to the star, where temperatures were too high for ammonia to condense, or subsequent thermal processing that destroyed original ammonia. The isotopic ratios would be the real prize, but those require extremely high spectral resolution and substantial signal strength. Isotopes of the same element like hydrogen, protium versus deuterium, or carbon-12 versus carbon-13 behave almost identically chemically, but have slightly different masses, which shifts emission wavelengths by tiny amounts. Measuring those shifts tells you about the environment where molecules formed because isotopic ratios vary with temperature, radiation field, and chemical pathways. For example, the deuterium to hydrogen ratio, D/H, in water varies between objects in our solar system. Comets from the Oort cloud typically have D/H ratios 23 times Earth's ocean value. Kuiper belt objects show a range of values. If we could measure D/H in 3I Atlas water, it would tell us whether its formation environment was similar to our solar system's comet-forming regions, or different in ways that reflect different stellar neighborhood conditions billions of years ago. Attempts to measure isotopic ratios in 2I/Borisov were only partially successful. Some carbon isotope measurements were obtained, but with large uncertainties. For 3I Atlas, the challenge is brightness and spectral resolution. The December Earth approach might provide the best opportunity: brighter apparent magnitude, longer integration times possible, larger telescopes with high-resolution spectrographs dedicated to the task. If successful, it would be a landmark measurement, the first definitive isotopic characterization of interstellar cometary material. But even without isotopic precision, the post-perihelion spectroscopic evolution is teaching us valuable lessons. It's showing us that interstellar comets aren't chemically uniform throughout. They have compositional gradients, surface versus interior differences, thermal processing that creates layers. It's demonstrating that perihelion passage doesn't just heat the surface, it fundamentally changes what we observe by exposing previously hidden material. And it's confirming that the basic chemistry water, carbon dioxide, carbon monoxide, organics, metals is similar between solar system comets and this interstellar visitor, suggesting universal processes in protoplanetary disk chemistry, regardless of which star system we're examining. The spectroscopic story of 3I Atlas will continue evolving through November-December and into 2026. Each spectrum captures a moment in its chemical evolution, a snapshot of which volatiles are sublimating at that distance and temperature. Stringing those snapshots together creates a chemical biography, this object's story told through molecules, the fingerprints of its birth preserved in ice for billions of years, now revealed in fleeting detail as it passes through our neighborhood for what might be the only time in human history. But chemistry is only part of the story. Morphology, the physical structure of the coma and tail, the patterns of jets and dust streams, provides complementary information about nucleus shape, rotation, and active region distribution. And post-perihelion morphology observations are revealing structures invisible during solar conjunction. Shape emerges from shadow. Structure reveals itself through asymmetry. And right now, As 3i Atlas moves away from perihelion with improving observational geometry, the shape and structure of its activity patterns are becoming visible in ways they simply weren't before late October. This isn't about the nucleus itself at 270 million kilometers distance even at closest Earth approach. The nucleus remains an unresolved point source, too small for any telescope to image directly. This is about the coma and tail, the enormous structures created by outgassing, which carry imprints of the hidden nucleus's properties like footprints, reveal the shape of a foot you never saw. Morphology observations began in earnest on November 1st, when ground-based telescopes recovered 3i Atlas after weeks lost in solar glare. The Nordic Optical Telescope in the Canary Islands acquired deep images showing coma structure. Palomar Observatory's 48-inch Schmidt telescope, part of the Zwicky Transient Facility normally hunting supernovae and asteroids, dedicated time to image 3i Atlas at multiple wavelengths. And amateur networks coordinated through organisations like the Comet section of the British Astronomical Association and the Comet Observation Database contributed hundreds of images from telescopes 10 to 16 inches in aperture, spread across latitudes and longitudes to provide continuous coverage as Earth rotates. What they're seeing is a symmetry. The coma isn't perfectly circular or symmetrical. There's elongation stretching in particular directions that changes over timescales of hours. There are brightness enhancements in specific regions of the coma, indicating concentrated dust or gas production from localized areas. And the tail structure shows streamers' narrow filaments within the broader tail that suggest episodic or jet-like ejection rather than smooth, continuous outgassing. Let's start with what asymmetric coma means physically. If the nucleus was spherical and outgassing uniformly across its entire surface, the coma would be perfectly circular when viewed from any angle. Brightness would decrease smoothly from center, where the nucleus is, to outer edges where coma thins out. We'd see classic concentric brightness contours like dropping a pebble in still water, create circular ripples. But real comets don't do that. Real comets have active region-specific areas where ice is exposed and sublimation is concentrated, and inactive regions where surface is sealed by dust mantles or lacks volatile ices. When active regions point toward the sun, they produce jets, concentrated streams of gas and dust. Those jets expand into space at speeds around 0.5 to 1.0 kilometers per second, slower than gas molecules individually, but fast enough that over hours and days they create visible structures extending thousands of kilometers from the nucleus. 3i Atlas shows elongation in coma structure oriented roughly in the sunward-anti-sunward direction, which is consistent with dayside outgassing. But there's also a symmetry perpendicular to that axis, suggesting active regions aren't symmetrically distributed relative to the rotation axis. This is actually typical. Most comets have heterogeneous surfaces with active regions concentrated in some areas, reflecting compositional variations or topographic features that focus sublimation. The time variability is particularly informative. Images separated by 6 to 8 hours show subtle changes in coma brightness distribution. Specific enhancements appear to rotate around the coma center. This is the signature of nucleus rotation. As the nucleus spins, active regions move in and out of sunlight, changing outgassing strength. The pattern of that change, when tracked over multiple rotation cycles, allows inference of rotation period and possibly axis orientation. Preliminary analysis suggests rotation periods somewhere in the range of 8 to 12 hours. That's based on the timescale over which brightness variations repeat and morphology patterns recur. It's not yet definitive. You need longer baseline observations with uninterrupted coverage to nail down precise period, but 8 to 12 hours is plausible for a comet nucleus a few kilometers across. It matches rotation periods measured for many solar system comets. Too fast and centrifugal forces would overcome weak gravity and tear the nucleus apart. Too slow, and it would be unusual, suggesting either very slow primordial rotation or tidal forces from close stellar encounters in the past that spun down rotation. The amplitude of brightness variation, how much brighter the comet appears at rotation. Maximum versus minimum constrains nucleus shape. If the nucleus were perfectly spherical, rotation wouldn't change brightness at all, because every view would show the same cross-sectional area. Brightness variation indicates the nucleus is elongated or irregular, so different rotation phases show different cross-sections catching sunlight. For 3i Atlas, brightness variations of 0.3 to 0.4 magnitudes have been reported. though disentangling intrinsic nucleus brightness changes from variable active region outgassing is tricky. An amplitude of 0.3 to 0.4 magnitudes corresponds to brightness factor of 1.3 to 1.4, which for a simple elongated ellipsoid translates to axis ratio, around 1.3 to 1.5, meaning if the long axis is 4 kilometers, the short axis might be 3 kilometers. That's modestly elongated, not dramatically, so like Oumuamua's extreme cigar shape, but enough to create observable photometric and morphological variations. Tail structure adds another layer. Tails form when dust ejected from the nucleus is pushed away by solar radiation pressure. Larger dust grains are pushed less, they lag behind and form curved tail structures. Smaller grains are pushed more, they stream away nearly radially from the sun. The distribution of grain sizes, the timing of ejection events, and the velocity of ejection all imprint on tail morphology. 3i Atlas shows a dust tail extending beyond 800,000 kilometers, roughly twice the Earth-Moon distance visible even in modest amateur telescopes. Within that broad tail, recent images reveal streamers, narrow linear features indicating concentrated dust ejection. These streamers could form from episodic outbursts, sudden increases in outgassing, that eject more dust over short periods, or from sustained jets that sweep through space as the nucleus rotates, like a lighthouse beam sweeping across fog. Comparing current tail morphology to pre-perihelion images reveals changes. Before perihelion, the tail was relatively smooth and symmetric. Post-perihelion images show more structure, more streamers, suggesting outgassing became more localized or variable through perihelion heating. This could reflect surface changes, maybe perihelion thermal stress, cracked through dust mantles exposing fresh ice in concentrated areas, creating new jets, or it could reflect our improved viewing angle, geometry changed post-perihelion, so features that were edging before might now be visible face-on. There's also the question of outbursts, sudden temporary brightness increases lasting hours to days, caused by discrete events like collapse of subsurface voids, fracturing that exposes fresh ice, or landslides triggered by thermal stress or outgassing pressure. Some solar system comets are prone to outbursts, others rarely exhibit them. Detection requires frequent monitoring to catch transient events. So far, no major outbursts have been definitively detected in 3i Atlas post-perihelion. The modest brightness excess we discussed earlier is gradual, not sudden. But monitoring continues, and December's closer approach will enable higher time-resolution observations. If outbursts occur, they'll be scientifically valuable. They provide windows into subsurface structure and composition, revealing material not normally accessible. Comparative context helps here. When spacecraft have visited comets Deep Impact at Tempel 1, Stardust at Wild 2, Rosetta at 67, P/Churyumov-Gerasimenko, they've revealed surfaces with incredible diversity. Active regions concentrated in specific areas, often associated with scarps, cliffs or depressions where sublimation undercuts structures. Inactive regions covered with meter-thick dust mantles, boulders and debris. Layered structures visible in cliff faces indicating compositional variations or multiple accretion events during formation. We can't see that level of detail on 3i Atlas, it's too far away, nucleus too small, but morphology observations let us infer that similar complexity exists. The jets, the asymmetry, the rotation signatures all point to a heterogeneous nucleus with distinct active and inactive regions, shaped by formation processes billions of years ago and modified by thermal processing during whatever orbital history it had before being ejected into interstellar space. There's a deeper question embedded in all this. How similar are interstellar comet nuclei to solar system comet nuclei? Do formation processes around other stars produce fundamentally similar objects, or are there systematic differences reflecting different stellar environments, different disk compositions, different timescales? Sample size is still tiny. We have detailed data on only 2 interstellar comets, 2I/Borisov and now 3I Atlas, plus the ambiguous case of Oumuamua, which may or may not have been a comet. 2I/Borisov showed activity patterns quite similar to solar system comets' jets, Comet symmetry, rotation signatures suggesting at least some interstellar comets are structurally similar to ours. 3I Atlas appears to fit the same pattern. If this similarity holds for future interstellar visitors, it would suggest protoplanetary disk processes are universal comets, formed through similar mechanisms, with similar structures and compositions, regardless of stellar mass, metallicity, or galactic environment, but we need more data. The Large Synoptic Survey Telescope LSST, now called Vera C. Rubin Observatory, begins full operations in 2025 and is expected to detect 1 to 2 interstellar objects per year. Some will be comets, others asteroids. Some will pass close enough for detailed study, others will be discovered already outbound. Over the next decade, we should accumulate a meaningful sample size, enough to start statistical comparisons and identify commonalities versus outliers. For now, 3i Atlas provides the most complete dataset we've yet obtained for an interstellar comet, and activity patterns are central to that dataset. Every image revealing jets, every spectrum capturing outgassing composition, every photometric point constraining rotation, they're pieces of a puzzle showing us what a comet from another star looks like when you watch it closely through perihelion passage and emergence. But 3i Atlas isn't done surprising us. Tomorrow brings the next major observational milestone, the Venus flyby. And while it won't be as close as the Mars passage in early October, it provides different viewing geometry and opportunities that matter for trajectory refinement and, potentially, gravitational mass estimates. Planetary encounters matter, even distant ones. Tomorrow, November 3rd, 2025, at approximately 1400 UTC, 3i Atlas will reach its closest point to Venus, 0.65 astronomical units, or about 97 million kilometers. That's nowhere near a close approach by spacecraft mission standards. That's more than 250 times the distance from Earth to Moon. Venus itself will appear as a bright but unremarkable dot in 3i Atlas's sky, if the comet had eyes to see. And yet this flyby is important for precision trajectory science, for testing orbital predictions, and potentially for constraining the comet's mass through gravitational perturbations. Let's start with what doesn't happen tomorrow. Venus currently has no active spacecraft in position to observe 3i Atlas directly. The Akatsuki orbiter, Japan's Venus climate mission operational since 2015, focuses its instruments on Venus's atmosphere ultraviolet and infrared images tracking cloud dynamics, lightning detectors, cameras monitoring the super-rotating upper atmosphere. Its orbit and instrument pointing are optimized for Venus observation, not for chasing faint comets passing at substantial distances, so we won't get spacecraft-based imaging or spectroscopy of 3i Atlas from Venus vantage point. What does happen is geometry change. From Earth's perspective, 3i Atlas and Venus will be angularly close in the sky tomorrow, separated by just a few degrees. This creates opportunities for astrometry precise position measurement. Venus's position is known with extraordinary accuracy, calculated from decades of radar ranging and spacecraft tracking. If we image 3i Atlas and Venus in the same telescope field of view, we can measure their relative positions to subarc-second precision, which translates to kilometre-level position accuracy at 3i Atlas's distance. That level of astrometric precision matters for trajectory refinement. Remember, orbital elements are calculated by fitting mathematical models to observe positions over time. The more positions you have, the better the fit. But equally important is geometric diversity observations from different angles at different times, sampling different parts of the orbit. Pre-perihelion observations were all from one general direction, Earth approaching Venus conjunction. Post-perihelion observations starting November 1st provide opposite geometry. Tomorrow's Venus flyby adds another data point with unique geometry. It's like triangulating a distant mountain peak. One measurement from one location tells you direction but not distance. Two measurements from different locations allow triangulation solve for distance. Three measurements from well-separated locations refine that solution and catch errors. Every additional observation from distinct geometry reduces uncertainty in the three-dimensional trajectory. There's also the gravitational perturbation question. When 3i Atlas passes Venus at 0, 65 AU, Venus's gravity pulls on it. The force is small, Venus's mass is only about 1/40th of a millionth the Sun's mass, and at 97 million kilometers distance, gravitational force drops to tiny fractions of percent compared to solar gravity. But it's not zero. That gravitational pull changes. 3i Atlas's trajectory by a tiny amount shifts its velocity by meters per second, changes arrival time at future waypoints by seconds. If we measure 3i Atlas's position before the flyby, then again after, with sufficient precision, we can detect that change. And here's the key. The magnitude of trajectory change depends not just on Venus's mass, which we know, but also on 3i Atlas's mass. Newton's third law: Venus pulls on 3i Atlas, 3i Atlas pulls on Venus. If 3i Atlas were very massive, its gravitational pullback on Venus would be measurable too, though in practice Venus is so much more massive that this reverse effect is negligible. But the deflection of 3i Atlas's trajectory by Venus depends on mass ratio and distance. For a given distance, more massive comet deflects, less higher inertia resists gravitational acceleration. Less massive comet deflects more lower inertia, means the same force produces larger acceleration. By measuring the actual deflection and comparing to predictions for different mass values, we constrain the comet's mass. The challenge is precision. At 0.65 astronomical units separation, gravitational deflection will be a few meters per second velocity change, corresponding to position shifts accumulating to perhaps hundreds of kilometers over days to weeks. That's measurable just barely with the astrometric precision achievable from coordinated ground-based observations. But it requires careful work, correcting for observational errors, accounting for non-gravitational forces from outgassing, separating gravitational perturbation from all other effects. Past comets have had masses estimated from planetary flybys. Halley's comet passed relatively close to Earth and Venus on various apparitions, allowing rough mass estimates. More recently, detailed tracking of spacecraft that performed comet flybys like Giotto at Halley, Deep Impact at Tempel 1 provided direct mass measurements from spacecraft trajectory changes. But for 3i Atlas, at these distances, mass determination from Venus flyby will have large uncertainty. The March 2026 Jupiter flyby will be much better for mass determination. Jupiter is far more massive than Venus, and closest approach distance of 0.36 astronomical units, while still large, produces stronger gravitational effect. If 3i Atlas's mass is toward the higher end of estimates, say 10 to the 13th kilograms for a 4-kilometer icy nucleus, Jupiter's gravity will deflect its trajectory measurably. Combined with precise pre- and post-flyby observations that will yield mass measurement with maybe 2030% uncertainty. Not laboratory precision, but scientifically useful. Mass combined with size gives density. Density tells us about composition and internal structure. Is 3i Atlas a dense, relatively rocky comet, maybe 1,000 to 1,500 kilograms per cubic meter, indicating significant rock content mixed with ice, similar to many solar system comets? Or is it low density, fluffy, porous, maybe 500 kilograms per cubic meter, indicating mostly ice with minimal rock, high porosity, weakly bound structure? Different formation scenarios predict different density ranges. Solar system comets span a range. Halley's comet has density around 600 kilograms per cubic meter, low density indicating high porosity or low rock fraction. 67P/Churyumov-Gerasimenko, visited by Rosetta, has density about 540 kilograms per cubic meter, also very low, indicating porous structure with voids making up much of the volume. Wild 2, visited by Stardust, has estimated density closer to 1,000 kilograms per cubic meter. If 3i Atlas fits in this range, it suggests interstellar comets share similar bulk properties. If it's significantly different, either much denser or much less dense, that hints at formation or evolutionary differences. But mass and density won't come from tomorrow's Venus flyby. What comes tomorrow is improved trajectory, validation that predictions are accurate, and data points that contribute to the overall orbital solution refined over months. It's incremental progress, unglamorous but essential. Science at its most fundamental measure: calculate, refine, measure again. From public engagement perspective, tomorrow is also an opportunity. Venus is easily visible to the naked eye right now, shining brilliantly in evening or morning sky depending on your location and time. While 3i Atlas itself is far too faint for naked eye observation, even in binoculars, knowing that an interstellar visitor is passing near that bright planet adds personal connection. You can look at Venus tomorrow evening and think, an object from another star system is near there right now, moving at 44 kilometers per second, carrying chemical fingerprints from a protoplanetary disk billions of years old. That connection between cosmic scale and human observation is part of what makes astronomy compelling. These aren't abstract events happening in mathematical space. They're real objects, real light, real photons that travelled across space and entered our telescopes carrying information we can decode. 3i Atlas is out there right now, at a specific location, doing specific things, outgassing, rotating, shedding dust, following laws of physics that apply everywhere in the universe. Amateur astronomers with telescopes 10 inches or larger and imaging equipment can contribute observations tomorrow. Coordinate with organisations like the International Comet Quarterly or the Comet section of the Association of Lunar and Planetary Observers. They're compiling databases of observations, including precise positions, brightness estimates, morphology sketches or images. Your observation could be the data point that refines some parameter, catches a transient event, or fills a time coverage gap in professional datasets. This is citizen science in action, not just educational outreach, but genuine scientific contribution. Professional astronomers can't observe continuously from every location on Earth. Clouds block views, daylight interrupts, telescope scheduling limits coverage. But a global network of amateurs, self-coordinated or organised through associations, provides distributed coverage that captures transient events and fills temporal gaps. Outbursts, brightness variations, jet activity changes, these can happen on our timescales and be missed if you're only observing once per night. After Venus, the next major milestone is December 19th, Earth closest approach. That's 7 weeks away, and during those weeks, 3i Atlas will steadily become better positioned for observation as solar elongation increases. By late November, it will be observable in reasonably dark sky. By early December, it will be accessible even to moderately light-polluted suburban locations for astrophotographers, and by mid-December, it will be at optimal position for the most intense observational campaign yet. But we're not just waiting passively. Observations continue daily, weather permitting. Spectroscopy accumulates, refining chemical understanding. Photometry tracks brightness evolution, testing whether that post-perihelion excess continues or fades. Morphology imaging captures coma and tail evolution. And all that data feeds into models being continuously updated by research groups, worldwide models predicting what December observations will show, what Jupiter flyby will reveal, what legacy dataset will remain after 3i Atlas fades beyond detection. Tomorrow's Venus flyby is one more step in that process. Not the most dramatic step that was perihelion survival. Not the most data-rich step that will be December's Earth approach, but an important step nonetheless, validating predictions, refining trajectory, moving the story forward. And in science, moving forward incrementally step by step is how we get from mystery to understanding. Mark your calendars. Set a reminder. Prepare your equipment. Because December 19th, 2025 represents the best opportunity, likely the only opportunity in your lifetime, to personally observe an interstellar visitor through your own telescope. On that date, 3i Atlas reaches closest approach to Earth, 1.80 astronomical units, approximately 270 million kilometers. That's 720 times the distance to the Moon. That's farther than Mars at its closest, but it's close enough and positioned favourably enough that amateur astronomers with 8-inch or larger telescopes, imaging equipment, and decent skies can capture it. This isn't about naked eye visibility. 3i Atlas at closest approach will be magnitude +12 to +13, depending on how its brightness evolution continues. That's roughly 250 to 600 times fainter than the faintest stars you can see with the naked eye under perfect dark sky conditions. It's about 25 to 50 times fainter than Pluto at its brightest. So forget casual stargazing. This requires equipment, technique, and dedication. But within those parameters, it's absolutely achievable. Thousands of amateur astronomers worldwide have the necessary equipment. Tens of thousands more have access through clubs, public observatories, or university facilities. And for those who don't have equipment, images captured by others and shared online through platforms like Cloudy Nights, Stargazer's Lounge, or the Comet Observation Database provide vicarious access to this historic event. Let's talk specifics. Where in the sky will it be? On December 19th, 3i Atlas will be positioned in the constellation Virgo, transitioning toward Leo over following weeks as it continues its outbound trajectory. From Northern Hemisphere mid-latitudes, think United States, Southern Europe, Japan that places it in the eastern sky before dawn, rising a few hours before sunrise. Observable window runs roughly 4 a.m. to 6 a.m. local time, depending on latitude and specific date. It will be at moderate altitude, not overhead, but not scraping the horizon either, so atmospheric turbulence and extinction won't be severe. From southern hemisphere Australia, South Africa, southern South America, the viewing is less optimal but still possible. Lower altitude above northern horizon, shorter observable window. Equatorial regions get reasonable compromise between northern and southern challenges. What will it look like? Visually, even through large telescopes, 3i Atlas will appear as a faint diffuse patch, a small fuzzy spot lacking distinct boundaries, gradually fading from centre outward. It won't look like a star. It won't show colours to the eye. Colours require brighter objects to trigger cone cells in the retina, and at this faintness, only rod cells respond, providing black and white vision. The tail, if visible at all, will appear as subtle elongation, a barely perceptible stretching in one direction. But photographically it transforms. CCD or CMOS cameras, whether dedicated astronomy cameras or modified DSLRs, can integrate light over minutes, stack multiple exposures, and faint details emerge. Coma structure becomes visible. Tail extends across the frame. Jets, if present and active, might appear as subtle asymmetries in brightness distribution. Post-processing stretching contrast, enhancing faint features, carefully balancing noise versus signal reveals a small but genuine comet, unmistakably non-stellar. Equipment recommendations. Telescope aperture 8 inches, 20 centimeters. Minimum, though 10 to 12 inches improves visibility significantly. Imaging camera capable of long exposures 5 to 10 minutes for a single frame. Mount capable of tracking at sidereal rate or better, with guiding to compensate for tracking errors over long exposures. Processing software to stack images and enhance faint features. Free options like Deep Sky Stacker work fine. Paid options like PixInsight provide more tools. For those without imaging equipment but with decent visual telescopes, averted vision technique helps. Look slightly away from where you expect the Comet. Peripheral vision uses more rod cells, more sensitive to faint light. Let your eyes dark adapt for at least 20 minutes. Use lowest magnification that still concentrates the comet's light, typically 30 times to 50 times for most telescopes. Be patient. Faint comet observation requires persistence. There's also the option to attempt spectroscopy. Amateur spectrographs devices that split light into spectra, like professional instruments, but smaller and less sensitive, can be attached to telescopes 10 inches or larger. With careful technique and sufficient exposure time, brighter emission lines might be detectable, CN, C2, possibly even water or CO2 if the comet remains active enough. This is advanced amateur work not for beginners, but absolutely within reach of skilled astrophotographers who've invested in spectrographic equipment. Why does amateur contribution matter? Because distributed observations provide continuous temporal coverage that professional facilities can't match. Large professional telescopes, Keck, Gemini, Very Large Telescope, Subaru have observing schedules packed with programs planned months or years in advance. They'll dedicate time to 3i Atlas, absolutely, but maybe 1 or 2 nights around closest approach. Amateur networks observe nightly, weather permitting, accumulating data that captures brightness variations, transient events, morphology changes over hours and days. Light curves, plots of brightness versus time benefit enormously from amateur data. Rotation period determination requires tracking brightness over multiple rotations, ideally with continuous coverage. Outburst detection needs frequent monitoring. Outbursts last hours to days, easily missed if you only observe once every few days. Professional observations provide high-quality spectra, detailed morphology, precise astrometry. Amateur observations provide cadence and coverage. Radar observations are a long shot, but worth mentioning. The Arecibo telescope in Puerto Rico, which performed radar observations of asteroids and comets for decades, collapsed in 2020 and is gone. But other radar facilities exist. Goldstone Deep Space Network antennas in California, Greenbank Telescope in West Virginia. Radar requires substantial radar cross-section, either large size or high reflectivity, and 3i Atlas at 270 million kilometers is pushing the limits. Most radar asteroid observations occur within a few million kilometers, but if brightness and cross-section estimates suggest it's feasible, Radar could provide direct ranging measure distance with centimetre precision and possibly even crude imaging if the nucleus is large enough and reflective enough. Whether radar succeeds or not, December's Earth approach gives the professional astronomy community its best chance for comprehensive characterization. High-resolution spectroscopy to search for weak emission lines, measure isotopic ratios, detect trace species, multi-wavelength photometry to separate dust and gas contributions, polarimetry to study dust grain properties' size, distribution, composition, shape, morphology imaging with large telescopes resolving coma structures smaller than 1,000 kilometers. This data will be published, analyzed, debated in scientific literature for years. Papers with titles like Post-perihelion Spectroscopic Evolution of 3I Atlas and Rotation and Activity of Interstellar Comet. 3I Atlas, during Earth approach, will appear in journals like Astronomy and Astrophysics, Icarus, the Astrophysical Journal. Doctoral theses will be written. Master's students will analyze subsets of data. Undergraduate research projects will compare 3I Atlas to solar system comets. But beyond the science, there's the personal connection. If you observe 3I Atlas yourself, capture it with your own camera, see it with your own eyes through your own telescope, you're witnessing something rare and historic. Interstellar objects bright enough for amateur observation are uncommon. Oumuamua was detected after perihelion, already faint and fading. 2I/Borisov was brighter, but peaked during Northern Hemisphere winter, when many experienced astrophotographers faced challenging weather. 3I Atlas in mid-December from northern mid-latitudes offers reasonable weather odds, pre-dawn timing that's manageable, and brightness within reach of common amateur equipment. You'll be part of a global community, observing simultaneously from different continents, comparing notes on discussion forums, sharing images on social media with hashtags like 3IATLAS and Interstellar Comet. You'll be contributing data even if just posting an image with timestamp and location. It contributes to coverage maps and activity monitoring. And you'll have a personal memory, a photograph, a logbook entry. December 19th, 2025. Observed interstellar comet 3I Atlas at closest approach. Captured 25-minute exposures, stacked in DSS, processed in Photoshop. Coma visible, tail faint but present. Magnitude approximately plus 12.5. First interstellar visitor I've personally observed. That's not abstract science. That's tangible connection to the universe beyond our solar system. That's photons from another star's comet, scattered off gas and dust, travelling 270 million kilometres, entering your telescope captured by your camera. Those photons carry information chemical composition, physical structure, thermal state encoded in wavelength distribution and intensity. You're decoding a message from interstellar space, one photon at a time. After December, 3I Atlas continues outbound. Brightness dims as distance increases and outgassing slows. By late December and into January 2026, it becomes challenging even for larger amateur telescopes. By February, it's primarily a professional telescope target. By March, as it approaches Jupiter, only the largest instruments track it. But March brings the final major milestone, the grand finale of 3I Atlas's journey through our solar system. The Jupiter flyby, where gravitational dynamics and Europa Clipper's trajectory create a scientifically rich and publicly compelling close to the story. March 16th, 2026. By then, 3I Atlas will have travelled billions of kilometres since its perihelion passage in October 2025. It will have cooled significantly as solar distance increased to nearly 2 astronomical units. Outgassing will have slowed, though not ceased. Carbon monoxide and other highly volatile species may still sublimate at Jupiter's distance. And on that date, it will pass closer to Jupiter than to any other planet in our solar system. 0.36 astronomical units, approximately 54 million kilometres. That's still an enormous distance. For comparison, Jupiter's moon Ganymede orbits at about 1 million kilometres from Jupiter, so 3I Atlas won't threaten any moons, won't pass through Jupiter's magnetosphere, won't create observable atmospheric effects. But 54 million kilometres from a planet with 318 times Earth's mass creates measurable gravitational interaction. And that interaction is scientifically valuable. Jupiter's gravity will perturb 3I Atlas's trajectory noticeably, Unlike the Venus flyby, where gravitational deflection was barely detectable, Jupiter's effect will shift velocity by tens of meters per second. Position at future dates will differ by thousands of kilometers compared to non-Jupiter trajectory. This perturbation, measured precisely before and after flyby, constrains 3I Atlas's mass far better than earlier planetary encounters. Here's the physics. Gravitational force between two objects depends on both masses and distance. F equals g times m1 times m2 divided by r squared. Jupiter's mass we know precisely 1.9 times 10 to the 27th kilograms. Distance we measure through observations. The acceleration experienced by 3I Atlas, which changes its velocity, depends on Jupiter's mass and distance, but also on 3I Atlas's mass through F equals ma. More massive comet requires more force to achieve same acceleration, so given fixed force from Jupiter, more massive comet experiences less velocity change. By measuring actual velocity change and comparing to calculations for different assumed comet masses, we solve for comet mass. If 3I Atlas is massive, say 10 to the power of 13 kilograms, equivalent to a 4-kilometer radius sphere of density 600 kilograms per cubic meter, Jupiter's gravity will deflect it less. If it's less massive, maybe 3 times 10 to the 12th kilograms, for smaller radius or lower density deflection will be greater. Observations will distinguish between these cases, providing mass estimate with uncertainty maybe 2030%. Combined with size estimates from brightness and assumptions about reflectivity, albedo mass gives density. And density is gold for understanding internal structure. Low density suggests high porosity, lots of internal voids, weakly bound structure. Medium density suggests mixed composition, ice and rock, moderate porosity. High density would suggest unusual composition, maybe more rock than typical comets, or compacted structure. There's another intriguing possibility for March 2026, Europa Clipper spacecraft encounters. Europa Clipper launched in October 2024 on a trajectory to Jupiter, where it arrives in April 2030 to begin studying Jupiter's moon Europa. But during its cruise phase, travelling through inner solar system before gravity-assist flybys at Earth and Venus accelerate it toward Jupiter, it follows a complex trajectory that might, depending on precise orbital timing, pass relatively near 3I Atlas's path. Europa Clipper carries dust detectors and mass spectrometers designed to analyze particles in Jupiter's environment, particularly material ejected from Europa's subsurface ocean. If Europa Clipper's trajectory intersects 3I Atlas's dust tail even at distances of hundreds of thousands to millions of kilometers, those detectors could sample interstellar cometary material directly. Not nucleus material, but coma and tail dust and gas. That would be a first. In situ sampling of interstellar comet composition. The likelihood depends on trajectories and mission planning. If intersection is possible but requires thruster burns that compromise primary mission to Europa, it won't happen. Europa science takes priority. If intersection is serendipitous, requiring no trajectory change, mission planners will eagerly activate dust detectors and collect data. As of late 2025, trajectory analysis is ongoing. By early 2026, we'll know if this opportunity exists. Even without spacecraft sampling, Jupiter flyby provides unique observational geometry. Earth-based telescopes will see 3I Atlas with Jupiter's disk as backdrop at certain moments, not transiting directly across Jupiter, but angularly very close. Jupiter's brightness makes astrometry challenging, but creates opportunity for differential measurements. Jupiter's moons, Io, Europa, Ganymede, Callisto, orbit with known periods and positions. If 3I Atlas passes behind one of them, an occultation, the timing of disappearance and reappearance measures position with extraordinary precision. Ground-based observations in March will face challenges. 3I Atlas will be magnitude +14 to +15, significantly fainter than December's +12 to +13. That puts it beyond reach of most amateur equipment, requiring professional telescopes or dedicated amateur setups with large aperture and imaging systems. But those facilities will be allocated. Observing proposals submitted months earlier will have been reviewed and approved, telescope time scheduled. Spectroscopy in March tests whether outgassing continues. At 2 astronomical units from Sun, solar heating is about 25% of what it was at perihelion. Water ice sublimation should have nearly ceased unless the nucleus is unusually dark or has exposed ice on surface. But carbon monoxide, which sublimates at far lower temperatures, active even beyond Jupiter's orbit in some solar system, comets might still produce detectable spectral lines. If CO emission is detected, it tells us 3I Atlas retains significant CO ice, characteristic of formation in cold outer regions of protoplanetary disk. After Jupiter flyby, 3I Atlas exits inner solar system for good. By April 2026, it will be beyond 2.5 astronomical units, dimming below magnitude +16. By mid-2026, only the largest telescopes, Keck, VLT, maybe Hubble Space Telescope if observing time is allocated, can track it. By late 2026, it fades into obscurity, lost in the vastness of space, returning to interstellar medium from which it came. Its journey won't stop. It will continue outbound at 44 kilometers per second relative to solar system, coasting through Oort cloud over thousands of years, eventually escaping Sun's gravitational influence entirely and resuming interstellar trajectory. It will travel for millions of years, perhaps billions, potentially encountering another star system where, if that system has astronomers, it might be detected again, studied again, wondered about again. But for us, March 2026 is the end, the last comprehensive observations, the final datasets. After that, 3I Atlas becomes a historical object studied through archived data, analysed in retrospective papers, compared to future interstellar visitors. Its legacy will be the lessons learned, the techniques refined, the protocols established for how to study such objects when they arrive, and they will arrive. LSST projections suggest 1 to 2 interstellar objects per year will be detected once the survey reaches full operation. Not all will be comets. Some will be asteroidal, inactive, revealing little. Not all will pass close enough for detailed study. Some will be discovered outbound, already leaving. But over years and decades, a sample will accumulate. 4I/?, 5I/?, 6I/?, each adding data points, each teaching new lessons, each revealing more about planet and comet formation around other stars. 3. I Atlas will be the object we compare them to. Is its brightness behaviour similar to 3I Atlas or different? Does spectroscopy match 3I Atlas's CO2 to water ratio? Is activity evolution consistent with 3I Atlas, or does it show something new? That's legacy becoming the standard against which novelty is measured. Jupiter flyby closes the observation window but opens the synthesis window. After March, when new observations cease, analysis intensifies. All the data photometry from dozens of observatories, spectroscopy across ultraviolet to infrared, morphology images revealing coma and tail evolution, trajectory measurements providing mass and non-gravitational forces will be compiled, cross-compared, modelled, interpreted. Controversies will emerge. Different research groups will favour different interpretations of ambiguous data. Papers will be published arguing for high-density nucleus, others for low density. Some will claim evidence for compositional anomalies, others will demonstrate those anomalies are observational artifacts. That's healthy scientific process debate drives rigour, forces careful examination of assumptions, ultimately converges on consensus or identifies areas where more data is needed. And that consensus, whatever it becomes, will shape our understanding of how common or rare objects like 3I Atlas are. If its composition, structure, and behaviour closely match solar system comets, that suggests protoplanetary disks produce similar outcomes universally. If significant differences exist, that opens questions about what conditions stellar mass, disk metallicity, giant planet migration create those differences. March 16, 2026 won't feel like an ending in real time. It's just another observation night, another dataset, another set of images and spectra added to the archive. But in hindsight, we'll recognise it as the last chapter of active observation, the moment when 3I Atlas transitioned from present tense mystery to past tense case study. That transition is bittersweet. We learned much, but we could have learned more. We answered questions but raised new ones. We watched an interstellar visitor pass through, and now it's leaving, carrying secrets we didn't manage to extract. But it confirmed something important. This is possible. Comprehensive study of interstellar objects is within our technological reach. We have the telescopes, the instruments, the coordination, the expertise. What we need is more targets, more opportunities, more visitors, and time will provide them. Let's return to the title, to the central question that drew you into this story. Just survived the sun, but something's different now. You've followed the journey through post-perihelion observations, brightness anomalies, trajectory refinements, spectroscopic evolution, activity patterns. Now it's time for synthesis. Now we answer directly. What does different actually mean? What changed? What surprised us? And crucially, what does that tell us about the nature of 3I Atlas and interstellar comets in general? Different does not mean unexplainable. It does not mean alien. It does not mean technology or intelligence or signals beaming toward Earth. If you hoped for that, and I understand the appeal of those narratives, the desire for universe to surprise us with unambiguous proof we're not alone, the data disappoints. Every observation, every spectrum, every brightness measurement is consistent with natural cometary behaviour. Complex, messy, sometimes unexpected natural behaviour, but natural nonetheless. Different means observational access changed. Before perihelion, 3I Atlas approached through good observational conditions visible in evening sky, well separated from sun, brightening as it approached. Then came solar conjunction, weeks of invisibility, lost in solar glare, inaccessible to ground-based telescopes. Post-perihelion, it emerged into different geometry morning sky. Solar elongation increasing daily, viewing angle changed relative to pre-perihelion. That geometry change alone alters what we see. Different active regions may be oriented toward Earth now compared to before. Tail geometry looks different from different viewing angles. What appeared symmetric before might appear structured now, not because tail changed, but because we're seeing it from different perspective. Brightness appears different partly because phase angle, the angle between sun, object and Earth, changed, affecting how much sunlight reflects toward us. Different means analytical depth increased. Before perihelion, we had 3 months of data, July through October, characterizing an object approaching peak solar heating. Those data allowed first-pass models, brightness as function of distance, spectrum showing dominant volatile species, trajectory establishing hyperbolic orbit and non-gravitational forces. But models built from approach phase data don't always accurately predict recession phase behavior, because thermal processes have lag, subsurface composition differs from surface, and outgassing responds to temperature history, not just instantaneous temperature. Post-perihelion observations test those models. The brightness excess, about 1 magnitude brighter than conservative predictions, reveals that outgassing didn't simply reverse the approach behavior. Something more complex is happening. Subsurface activation, thermal inertia, rotation effects, or some combination. That complexity is interesting. It tells us 3I Atlas isn't a simple, homogeneous iceberg that heats and cools predictably. It's a structured, layered, heterogeneous object with interior properties different from surface. Different means subsurface composition revealed. The spectroscopic shift from CO2 dominated to increasing water contribution tells a thermal story. Surface layers were CO2-rich either primordial composition or surface frost accumulated during interstellar travel. Perihelion heating sublimated that CO2 preferentially because it's more volatile. Now post-perihelion, thermal wave has penetrated deeper, exposing subsurface layers that are water-rich. Those layers probably better represent original composition from formation around another star, less modified by interstellar exposure. If this interpretation holds, 3I Atlas's interior composition is similar to solar system comets, formed in outer regions of our protoplanetary disk, Kuiper belt objects, Oort cloud comets which are waterous dominated with CO2, CO and other volatiles mixed in. That similarity is profound. It suggests the chemical processes that built comets around our Sun operate the same way around other stars. Carbon, oxygen, hydrogen, the building blocks of water, carbon dioxide, organics combine into ices under cold conditions universally. Interstellar comets aren't exotic. They're familiar cousins formed under similar physics. Different means activity evolution continues. The jets, the coma asymmetry, the tail structures, the brightness variations all indicate ongoing dynamic outgassing. Some comets shut down post-perihelion as surface seals over with dust mantles. 3I Atlas remains active, implying volatile reserves weren't depleted. Surface hasn't sealed completely, nucleus retains ability to produce gas and dust as it moves outbound. That activity will gradually decline as solar distance increases and temperature drops, but it should persist through December's Earth approach and perhaps into early 2026. Active comets provide ongoing data streams. Every observation adds information. Inactive comets become static one brightness measurement, one spectrum if you caught it while active. Done. 3i Atlas's continued activity means we'll track its evolution over 6 months from perihelion through Jupiter flyby, watching how brightness, spectroscopy and morphology respond to decreasing solar heating. That long baseline dataset will be invaluable for modelling cometary thermal physics and outgassing dynamics. Different means precision improved, trajectory uncertainty decreased from thousands of kilometres to hundreds, brightness law parameters refined from rough fits to precise power law exponents, spectroscopic line ratios measured with better signal-to-noise than perihelion data allowed, rotation period constrained from unknown to 812 hours, likely, nucleus shape inferred from brightness variation amplitude, non-gravitational acceleration parameters updated. Each of these refinements shrinks uncertainty, narrows the range of viable models, eliminates some hypotheses and strengthens others. Before perihelion, we could speculate broadly about 3i Atlas's properties. After perihelion, speculation becomes constrained by data. That's progress. That's how science converts mystery into understanding incrementally. But here's the critical point. Different now, compared to before, perihelion doesn't mean different compared to expectations for natural cometary behaviour. Everything observed falls within the broad envelope of what comets can do. The brightness excess is large for a simple power law model, but small compared to comets that undergo major outbursts. The spectroscopic shift from CO2 to water is textbook thermal evolution, documented in multiple solar system comets. The activity patterns jets, coma asymmetry, rotation match what spacecraft missions have revealed for solar system comet nuclei. If you were hoping for different to mean something extraordinary, something that challenges our understanding of what comets are or how they form, the data doesn't deliver. And that's not disappointing, it's reassuring. It means the universe operates on consistent principles. Stars form, protoplanetary disks form around them, planets and comets accrete from disk material, gravitational interactions eject some comets into interstellar space. Those comets travel for millions of years until they encounter another star system, and when they do, they behave like the comets native to that system because they formed through the same processes. Different ultimately means we're learning. Before perihelion, 3i Atlas was characterized from approach data only. Now we have approach, perihelion, and recession data. That complete trajectory through solar heating cycle provides comprehensive picture how composition changes with temperature, how outgassing responds to heating and cooling, how nucleus structure affects observables, how an interstellar comet compares to solar system comets across all phases of solar encounter. The comparison to 2I/Borisov is instructive. 2I/Borisov also showed CO2 and water in its spectrum, also remained active post-perihelion, also exhibited jets and coma structures. But 2I Borisov's perihelion was 2.0 astronomical units, significantly farther from Sun than 3i Atlas's 1.36 astronomical units. So 3i Atlas experienced stronger heating, reached higher temperatures, potentially revealed deeper interior layers. It's the closest perihelion passage of an interstellar comet we've comprehensively observed. That makes its post-perihelion data uniquely valuable for understanding thermal response. When 4I/? is discovered and passes through inner solar system, whenever that happens, we'll compare to 3i Atlas. If its perihelion is similar distance, does it show similar CO2 to water evolution? If its brightness evolution differs, is that because of different composition, different size, different structure? If activity patterns are similar, that suggests interstellar comets are a relatively homogeneous population. If activity patterns vary widely, that suggests diversity reflecting different formation environments or evolutionary histories. 3i Atlas is establishing the baseline for that comparison. It's showing us what normal looks like for an interstellar comet passing at 1.36 astronomical units perihelion. Future objects will be measured against this standard, and when enough objects accumulate maybe a dozen, maybe 24 over coming decades, we'll be able to categorize them, identify common features versus outliers, correlate properties with incoming velocity or trajectory inclination or brightness evolution. That's the long game of interstellar object science. Accumulate sample, identify patterns, infer formation and evolution processes for comets and asteroids around other stars. 3i Atlas is data point number 3. Oumuamua, 2i/Borisov, now 3i Atlas. Each additional object doubles our statistical power when sample size is small. By the time we reach 10 objects, we'll start seeing meaningful patterns. By 20, we'll have preliminary taxonomy. By 50, robust statistical conclusions. But all of that depends on detecting future visitors, which depends on survey telescopes. LSST is the game-changer wide field, rapid cadence, deep limiting magnitude. It will find interstellar objects that previous surveys would have missed. It will detect them earlier in their trajectories, allowing longer observational baselines. It will provide discovery alerts that trigger follow-up observations by specialized facilities, and each discovery will reference 3i Atlas. Brightness evolution similar to 3i Atlas. Spectroscopy different from 3i Atlas, showing X instead of Y. Activity patterns match 3i Atlas post-perihelion behaviour. That's legacy becoming the archetype, the reference case, the object future studies build upon. So what does different now mean after synthesizing all post-perihelion data? It means we understand 3i Atlas better now than before perihelion. It means reality proved more complex than the initial models captured, which is expected and welcomed because complexity is where learning happens. It means the object behaves naturally, consistently with cometary physics, validating our understanding of how these objects work. And it means the story didn't end with perihelion survival, the story continues, evolving, revealing new details, teaching new lessons, right up until 3i Atlas fades beyond detection and passes into history. But even then, the story doesn't truly end, because 3i Atlas changed us. It gave us experience, data, techniques, confidence. It proved that comprehensive study of interstellar visitors is possible, worthwhile, scientifically rich, and it left us waiting, watching, ready for the next visitor whenever and wherever it appears to add another chapter to our growing understanding of the universe beyond our solar system. Step back, zoom out, look beyond the specific data points, beyond the spectral lines and brightness curves and trajectory calculations, and ask the question that actually matters. Why does any of this matter? Why dedicate telescope time, research funding, human effort to tracking one comet that poses no threat, offers no resources and will disappear forever in months? Why do post-perihelion observations of 3i Atlas matter beyond academic curiosity? The answer operates on multiple levels, from practical to philosophical. Start with the practical. Every interstellar visitor we study comprehensively improves our protocols for planetary defense. Not that 3i Atlas threatens Earth, it doesn't, but the next interstellar object might. The techniques we refine tracking, 3i Atlas rapid trajectory determination, non-gravitational acceleration modelling, brightness prediction, compositional characterization are exactly the techniques needed to assess whether an incoming object is dangerous. Most near-Earth objects are asteroids rocky, inactive, following purely gravitational trajectories that are straightforward to predict. But some are comets or dormant comets that might activate if they pass close to Sun. Outgassing creates forces that change trajectories in ways pure gravity doesn't predict. If we don't account for those forces accurately, impact predictions become unreliable. False alarms cause panic. Missed threats cause disasters. 3i Atlas provides ground truth data for outgassing models. We observe outgassing directly through brightness, spectroscopy, morphology. We measure trajectory deviations caused by that outgassing. We correlate the two, how much outgassing produces how much trajectory change for an object of this size and activity level. Those correlations, validated against real data, improve models that assess future objects. The International Asteroid Warning Network, IAWN, and national space agencies like NASA, ESA, JAXA coordinate observations of potentially hazardous objects. They maintain catalogues, calculate trajectories, assess risks, issue warnings if needed. Every object observed adds to their databases, refines their algorithms. 3i Atlas, despite being no threat itself, is a test case for tracking active objects at moderate solar distances. The fact that post-perihelion trajectory matches refined predictions within error bars validates that current tracking technology works when outgassing is moderate. If trajectory had deviated wildly, that would expose gaps in understanding requiring urgent attention. Beyond planetary defense, there's comparative planetology. Every star we can observe formed from a collapsing molecular cloud, possibly within a star cluster, possibly in isolation. Protoplanetary disks formed from material not consumed by the stardust and gas settling into flattened rotating structures. Within those disks, dust grains collided and stuck together, growing into pebbles, boulders, planetesimals, eventually planets and leftover comets. That's our solar system's formation story. Is it universal? Do all stars form planets and comets through similar processes? Do different stellar masses, M dwarfs versus sun-like stars versus massive A stars, produce different planetary architectures? Does disk metallicity, abundance of elements heavier than helium, affect what kinds of planets and comets form? We can't directly observe exoplanet formation happening. Processes take millions of years. We can detect exoplanets through transits, radial velocity, direct imaging, but those techniques tell us about final products, not formation processes. Interstellar comets offer a different window. Their composition, especially isotopic ratios if we could measure them, precisely records formation conditions, temperature, radiation field, chemical pathways. By studying comets from multiple star systems, we can start comparing formation environments, identifying commonalities and differences, building empirical understanding of how planet formation works universally. 3I Atlas's composition, particularly the water/CO2 ratio, organic content and nickel presence, resembles solar system comets formed in cold outer regions. If next few interstellar visitors show similar composition, that suggests cold outer disk regions universally produce waterous comets with similar volatile mixtures. If composition varies widely, that suggests disk conditions, temperature gradients, chemical compositions, stellar radiation fields differ significantly between stars, affecting what comets form. Sample size is currently tiny 3 objects if we count Oumuamua, 2 clear comets if we don't. But over next decade, LSST will increase that sample meaningfully. Each new object will be compared to 3I Atlas and 2I/Borisov, expanding our statistical understanding. Within 20 years, we might have enough data to make robust claims about whether interstellar comets are uniform or diverse, whether our solar system is typical or unusual, whether planet formation is a convergent process that produces similar outcomes everywhere, or divergent process sensitive to initial conditions. There's also the methodological value. 3I Atlas is a proving ground for observational techniques that will be used on future missions. Spectroscopic detection of weak emission lines, morphology analysis revealing jets and rotation, thermal modelling predicting brightness evolution. These techniques, refined on 3I Atlas, will transfer directly to future interstellar visitors or to comets in our own solar system that haven't been well studied yet. Public engagement matters too, though it's often dismissed as secondary. But inspiring the public, especially young people considering STEM careers, has long-term value that's hard to quantify, but undeniably real. 3I Atlas captured public attention because it's tangible and accessible. Not everyone can understand galaxy evolution or quantum entanglement, but everyone can grasp comet from another star system passing through ours. That narrative hooks curiosity. The scientific investigation then shows what modern astronomy can do: detect faint objects millions of kilometers away, determine composition from light, predict trajectories, coordinate international observations. Young people following this story might think, I could do that. I could be the astronomer who discovers the next interstellar visitor, or interprets its spectrum, or builds better detection telescopes. Career choices often trace back to moments of inspiration: a planetary flyby, a Hubble image, a teacher who made astronomy come alive. 3I Atlas is creating those moments for people paying attention right now. And philosophically, there's the perspective shift. For most of human history, comet meant object from our solar system. Even after we understood solar system architecture, comets were always ours orbiting our sun, occasionally visiting inner solar system where we could see them. Oumuamua in 2017 shattered that assumption. Interstellar objects pass through regularly. We just never had instruments sensitive enough to detect them before. Now, 3I Atlas reinforces the new reality. Interstellar visitors are detectable, observable, characterizable. The universe isn't divided into isolated solar systems that never interact. Instead, ejected comets and asteroids travel between stars, sampling different environments, potentially even transferring material organic molecules, maybe amino acids, possibly even dormant microbes if panspermia hypothesis has merit between stellar systems. That's profound. It means our solar system isn't sealed off from the rest of the galaxy. Material enters, material leaves. Every interstellar comet that passes through carries molecules formed around another star, materials from another protoplanetary disk. Some of those molecules might land on Earth 3I Atlas as shedding dust particles, some of which will eventually encounter Earth's orbit years or decades from now, raining down as micrometeorites. We'll breathe atoms that originated around another star. That's cosmic connection made literal. And looking forward, the technological curve is steep. LSST is just beginning. Next generation space telescopes. James Webb's successors, proposed missions like LUVOIR or HabEx, will have sensitivity and resolution that make 3I Atlas scale observations routine for interstellar visitors. Techniques like fast response spectroscopy, rapid telescope scheduling, real-time orbit determination will mature. Coordination between ground-based and space-based assets will improve. Within decades, intercepting an interstellar visitor with spacecraft becomes feasible. Mission concepts exist. Project Lyra, for example, studied how to send a probe to Oumuamua despite it having already left inner solar system. Fast response missions with powerful propulsion could launch within months of interstellar object discovery, intercept during solar system passage, perform flybys or even rendezvous, return samples to Earth. Imagine sample return from interstellar comet. Not just spectroscopy from Earth actual material, physical samples, analysed with laboratory instruments, isotopic ratios measured precisely, organic molecules sequenced, minerals identified. That would be transformative for understanding planetary formation around other stars. And it's achievable technically with sufficient funding and will. 3I Atlas won't be that sample return target it's leaving, and mission concept to launch timeline is too long. But it establishes proof of concept that such missions would be scientifically valuable. It demonstrates the kinds of questions we can ask with remote observations and the kinds of answers we'd get from direct sampling. It builds the scientific and public case for funding such missions. So why do post-perihelion observations matter? Because they complete the story. Because they test models. Because they reveal subsurface composition. Because they refine techniques. Because they engage the public. Because they shift perspective, because they prepare us for next visitor, because they're part of humanity's ongoing project to understand the universe we inhabit, one photon and one data point at a time. 3I Atlas survived the sun. Something's different now, we understand more. We've refined our tools, we're ready for next visitor, and the universe, vast and full of wonders, will eventually send that next visitor our way. When it arrives, we'll be watching, we'll be ready, and we'll remember 3I Atlas as the object that taught us how to look.